My name is Tyler,
I'm Daniel.
and our topic is energy and light. All electromagnetic radiation or light energy travels at a particular wavelength and carries a certain amount of energy.
In this video, we will be explaining the differences between short and long wavelengths.
But first things first, what is light energy?
The sun emits an enormous amount of electromagnetic radiation, solar or light energy. Humans can only see a fraction of the energy, which is referred to as visible light. The manner in which solar energy travels is described as waves. Scientists can determine the amount of energy of a wave by measuring its wavelength. The distance between each consecutive points of a wave, such as from crest to crest or from trough to trough.
Now that we have a basic understanding of light energy, we can talk about the electromagnetic spectrum.
Visible light constitutes only one of the many types of electromagnetic radiation emitted from the sun and other stars. The electromagnetic spectrum is the range of all possible frequencies of radiation. The electromagnetic spectrum shows several types of electromagnetic radiation originating from the sun, including X-rays and ultraviolet rays. The higher energy waves can penetrate tissues and do damage to cells and DNA, which explains why both X-rays and UV rays can be harmful to living organisms. Scientists differentiate the various types of radiant energy from the sun, which the electromagnetic spectrum. The difference between each wavelength relates to the amount of energy carried by them.
A great example of the electromagnetic spectrum is the flame test lab. We burned sodium chloride, or NaCl. We observed that it burned a bright orange. The color of the flame was produced when the sodium chloride was heated to a certain level. The electrons jumped to a higher energy level, making them unstable. For them to return to a stable state, they had to give off the energy they received. The electrons did this by emitting waves in the form of light particles that we perceive as the color orange.
Light energy and the electromagnetic spectrum are great, but we're going to have to go more in detail if we want to truly learn and understand energy and light. Time to learn about particles and waves.
Physics experiments over the past 100 years have demonstrated that light has a dual nature. In many instances, it is easier to represent light as a particle phenomenon, thinking of light as packets of energy that we call photons. Now, in the way of thinking, not all photons are created equal, at least in terms of how much energy they contain. Each photon of X-ray light contains a lot of energy in comparison with, say, an optical or radio photon. It is this energy content per photon that is one of the distinguishing characteristics of the different ranges of light described above. Even though it is not strictly correct, it is hard not to think of a beam of light as a collection of little light bullets all strung together in a row.
The other way of representing light is as a wave phenomenon. If you're having trouble grasping the context, here's an example. When you play a high note and a low note on the piano, they both produce a sound, but the main thing that is different between the two notes is the frequency of the vibrating string producing the sound waves. The faster the vibration, the higher the pitch of the note. Now imagine the sound waves themselves. Instead of the vibrating string, we would find that the higher pitched notes have shorter wavelengths, or distance between each consecutive wave. Like blue light and red light are both just light, but the blue light has a higher frequency of vibration, or a shorter wavelength, than the red light.
An example of photons and wavelengths are X-rays. The X-ray machine produces a very concentrated beam of electrons, also known as X-ray photons. The X-ray photons have a short, fast wavelength. It allows them to pass through low-density materials such as muscle, organs, and skin. However, high-density materials such as bones and foreign objects ricochet the photons back, allowing a clear picture of like a photograph. The movement of the waves can change the particle's position and the electromagnetic spectrum, which can create different types of waves.
This has been our presentation on energy and light. Through our understanding, we hope to learn more about it. Thanks.